Change it to a polite thing.
Yeah, that's really right. This is being enough. I need to really go.
Okay, so I wanted to show you a weird open set in the usual topology, because open doesn't mean that it's an open interval. It just means what you have, that you can write any set as a union of open intervals. So that, because it's generated by basis. So a weird open set. There's all kinds of things you can do with the Cantor set that make it like, you can make something called a fat Cantor set. So you can use the Cantor set as a basis to make or an idea. I don't want to use the same word of basis, but you can use it to make up stuff that looks strange. So if you think about the Cantor set, if you haven't seen it, all it is you take the unit interval and you remove the middle third. So from 1/3 to 2/3, I'm going to remove that open interval. Remove that guy. And so I get now these two sticks. And then you consider that stick to be the unit interval again. Well, I mean, if you're a dynamicist like I am, you think of that to be a unit interval again. Topologically, it is, right? Because any piece is really, if you have Plato, you can stretch it to be back to the original, like 0, 1. But that aside, I'm going to just do it again. I'm going to remove the middle thirds. And so this is my set A0, A1. A2 would be from 1 to 1/9. And then I'd get 4 pieces, 2/9 to 3/9. Oh, sorry, I didn't know.
Is it 1 to 1?
Yeah, so it's like I'm just taking out the middle third. I'm just pulling out the middle third and keeping what remains. This is the definition of Cantor set. You're just keeping out.
On one side, this is.
Oh, 0, sorry. And so it's 0 here. And so forth. I don't want to deal with fractions. I think there's probably apps online that'll show you like the removal of these things. So the Cantor set has these properties that make it just a cool counterexample for a lot of things, or an example for a lot of things. It's closed. It's what we call it has measure 0. So it, like, if you think of sets as probability of sets, the probability of that set, there's something called a measure that's used for probability. That's 0. So there's almost nothing in it, but there's something in it. And so it's infinite. So you have like stuff in it, but there's nothing in it. So that stuff that you get at the bottom, they call that Cantor dust. So keep going down to the bottom, Cantor dust. But it doesn't have stuff too. Does that make sense? It just. And it's a fractal. It's a great example of a fractal, because you're doing something self-similar. You're pulling the middle thirds every time, so you get these lines that are starting to break up that original interval, but you have mini versions that look like that original interval, and you're doing that process over and over. So it's a great example for a lot of things. What's left behind, though, they're all open intervals. So if you look at the complement of what I'm taking out, they're all open. one third, the open interval, 1/3 to 2/3, the open interval from 1/9 to 2/9, and so forth. So if I union up all the stuff I left behind, that's open because it's the union of open intervals that makes it open. Stuff is an official math word. The complement, like what the things I removed, right? So that would be 1/3 to 2/3 union, 1/9 to 2/9. Oops, I say 2/9 and I write something else. Hand-eye coordination is not working today. And 1/9 to 2/9 union dot 7/9 to 8/9. The stuff you removed. The stuff in between the dust is open because it can be represented as a union of open intervals. There's all kinds of stuff. Usually the strange intervals that or strange sets that you get come from probability theory. So you can get like with Brownian in motion, you can get some like weird looking sets showing up. That's where you get the weird example of something that's continuous everywhere and differentiable nowhere. You'll make up those examples. They come from probability. There is a beast that is continuous everywhere and has a derivative nowhere. I don't know if you can make up an example except outside of probability, but that's the only ones I've seen. The Cantor set is closed. The Cantor set has some unusual properties too. Like it has that probability 0, meaning that there's nothing in there, but it's got something in there because there's an infinite, it's infinite. So you have something in there, but it kind of has nothing in there. It's countable, countably infinite, what's left, and it's closed. Countably infinite and closed, but has measure 0.
Closed.
We don't have a definition yet. You'll get it.
But it's not just the opposite.
No, that's not even true for the usual topology. If I take an open, like a couple open intervals and union them so they have some overlap, I don't get that the complement is closed. You can get Clopin sets, like half open and half closed.
No, could you repeat what you said about the complement of the communities? There was something about a complement.
The complement of the Cantor set?
Yes.
That one is open. So what I just did, that's an open set, but by definition of a topology generated by a basis, I got it. Like as soon as I just take those things I just removed and union them up, they're a union of open intervals.
Okay,
which
so when you say everything left behind,
that's open. That's a weird open. Yeah, everything left behind is the complement inside the interval 0, 1. Okay, so this is my favorite example. This is the reason I like this book. I haven't even had time to like look at the intersection of sets yet, but as soon as I do, I'm going to text you, respond you right away if there's a no, don't come on this Tuesday, so I can send him back a date. And I didn't tell him the most important thing, that we meet at 7:40 in the morning.
Oh.
So I'm going to ask him if he'll come to Thayer, and I'll see if I can use my NIH money to get him a room there. And then, because that's uncomfortable for most people. 7:40 in the morning is uncomfortable for most mathematicians. On your end, can you see if we can sequester a table for topologies, students and him? Well, you'll need a date first, though.
Have pizza, we can go to lunch and then come here. just like right back to back.
Let me talk to Colonel Scaletti first about that. Yeah, I do think it like. When I tell people I teach at 7:40, they're like, how do you do that? Like, well, you teach at 8 at night, which I just hated that. I taught topology at 8 at night after teaching combinatorics at 5:30. I didn't know who I was or what I was doing, like after some time. Like it's so late at night. We ended class at 11. We'd have it once a week, 8 o'clock to 11 o'clock, topology. Brutal. All right, this is my favorite example. This is why I love this book. Of a basis, and I gave you homework problems off of this. Oops. So this is called the digital line topology, and it's defined by its basis. If n is odd, and n minus 1, and n plus 1, if n is even. Yes, I have a note here that did I do something with you guys here for this? Okay, yes. Yes, this is a digital line topology. It's the basis for it. So the basis is going to be B of n such that n belongs to Z. Well, it's not, this is not called the digital line topology. So I'll wait till you take those notes and I'll move to the next slide. Yes. What is the basis? So this is the basis for the digital line topology. And I don't know if you remember the first time you wrote a proof or did anything with pure mathematics, but that rush, there's a rush. So I'm like I'm holding back those foundation students, like, let me just write the proof. Like, no, slow down, write down what you like, get your puzzle pieces all expanded. And then, they write stuff that's not a real proof, and you have to go back. Like, you skipped all these steps. It's like you have puzzle pieces and they're in a box, and you don't open the box. You're trying to put the puzzle together without the puzzle pieces. You need to put the puzzle pieces out there. This is like the first step. You try to look at a weird set like this. And that's why I'm giving them these kind of weird sets to think about in that class. Because if you just use set theory with easy sets, they're just gonna want to just go straight to writing proofs. You have to show them like there's weird stuff out there. It's like when you're little and they show you like x squared for every example. Like, well, that's easy. And then your homework is find the derivative of square root of sine of x squared minus 1. That's like, wait a minute, I thought this was easy. Okay, so I
didn't learn the limit definition of like my second.
Limit definition is best. It's the best.
Yeah, this works. Yeah.
So the topology.
I had a really terrible calculus teacher my first year of calculus. I was like, I don't know if people come to me for like tutoring stuff. Yeah, I knew that class inside and out. That's how I was done with it. Luckily, I got a new one for my second year. 2-3 years back.
My calculus instructor told me that we don't want math.
I'm trying to teach you, but looks like it was
That was super fun.
she was very.
All right. So now I gave you an in-class assignment to deal with this topology. I'm going to go back to the previous slide so you can look at the basis elements. And I ask you some of those same questions I asked you about the usual topology. Is Z in there? Is Q in there? What's in there? See if you can like play around with these sets and describe what is in there. So you asked about point set. Like, I like these kind of examples because it's different than point set, and it makes you think more topologically than point set does. All right. Once you have that written, I can go back to the previous. Do you need that one? I'll blast that part up on the board.